I stop and do nothing. Nothing happens. I'm thinking about nothing. I listen to the passing of time. This is time, familiar and intimate. And this is the topic of the book I want to talk to you about for about half an hour. But first of all, let me thank you for all being here. And let me apologize for this voice. I was in California just before coming here, and I went kayaking. And I rolled over in the ocean, which is icy, so I just no voice whatsoever. I hope it lasts for 1 hour. I still think I'm 20, which of course I'm not anymore, because time is real in spite of everything. And actually, let me thank C-SPAN, which is here. I'm European, I live in Europe now, but I spent 10 years in America. Great 10 years, fantastic 10 years. And the only TV channel I was watching is C-SPAN. I was in adoration of C-SPAN, of the fixed camera language. I found it a fantastic way of using TV. So hello, C-SPAN. All right. So I wrote this book after finishing my previous book, which was the 7 Brief Lessons of Physics, that some of you may have read, which has something in common with this book, but is also a completely different book. The 7 Brief Lessons were a overview, a large panoramics of physics of the last century, and a very compressed one where I tried to sort of extract from the main chapters of modern physics, relativity, quantum mechanics, cosmology, what I saw the main message, the core, and try to strip away all which was irrelevant and give a perspective on it, which is my perspective. I've been working in physics for all my life, and I have my own way of viewing things. So it was a book that I addressed to everybody. It was written for somebody who knew nothing about science. But somehow I got funny reactions. It was liked a lot by people who know nothing about science and people who know these things in depth, and much less by the students who just came out from school and had learned these things. Because I had simplified very much, taking away very much. So typically, the biggest criticism I got were, you talk about quantum mechanics and don't even mention the Schrödinger equation, things like that. What I was trying to do is to communicate what I think is the most, the key novelty in our understanding of the world that came from fundamental physics, instead of a lot of information. Now this I also try to do with this book, but instead of a large panoramic, it just focused on a single problem, a single issue. It was not easy for me to go back to writing after the 7 lessons, because the 7 lessons were very widely read, and somehow I did not want to repeat the same thing. I thought my reader wanted more than just repeating a formula. And I decided that what I could do is to talk about the problem that has most attracted me and fascinated me through my career as a scientist. I do quantum gravity, that's what the job, that's what I'm paid for. So the problem of combining, you're asking me to speak louder. Okay. I do what I can with my voice. I take the microphone closer to my mouth. I do quantum gravity, so the problem of combining general relativity with quantum mechanics. And to do that, one side of the problem is to write the equations, the mathematics that make a consistent story. But the other side of the story, and I would say the most interesting side of the story, is the conceptual change required to do quantum gravity. Quantum gravity means the quantum aspect of gravity. Gravity, we learned from Newton, is space and time, structural space and time. So this is a quantum structural space and time, which means in particular that we have to rethink space and time. And so all my life, somehow, 30 years of my life, I've worked going around this thoughts, what it means, what we mean by space and what we mean by time. And it's a fascinating story. It's an incomplete story, and that's the story of the book. And it's a story in many chapters, in many steps, because to a large extent, the first part of the book, if you want, I tell what we have learned already about time. Since the work of Einstein, which is a century ago, but even before, with statistical mechanics and thermodynamics and entropy, physics has learned facts about time which I believe are not known by the large public yet, for a number of reasons. One being that it's only today that these discoveries become relevant for technology, for observations. And the other because they're hard, they're strongly counterintuitive. So we know that we know for a fact that time is different, works differently from the way we usually think about time. And that's the first part of the book. Somehow trying to say in the clearest possible way what is it in our common view about time which is wrong. Now, of course, it's not wrong in the sense that we should change it for our daily life. Time in our daily life is what we know it is and what we think it is. But the concept of time we have is not appropriate to describe the world when we go just beyond our daily life. When we go in the small, when we go in the large, when we describe things that move fast, or simply when we measure time more precisely. So that's how we think time, right? It's a long line. That's time. We are here, and that's the past, the faraway past. The other side is the future, and it's a long sequence of instants, a long sequence of presents, one after the other one, and we are all in a moment of time. We are all in a point of this long line. The intervals are measured by clocks. Clocks go all at the same speed, and all the universe is in a now, and then another now, and then another now. The past is completely different from the future. It's fixed. The future is open. Almost everything I've said is wrong. Completely wrong. Let me start from the simplest thing. We measure time with clocks, watches, okay? And we know for a fact that... can I borrow somebody? Sir, can I borrow your watch? You mind?
You will give it back, right?
I'm Italian, but in spite of that, I promise. Please trust me. You have a lot of witnesses. So if these were much better clocks than what they are, no offense, this is a very good clock. It was much better than this. We could note the following. They indicate the same time. I raise one. I count 1, 2, 3, 4, I wait a little bit, I bring it back, I look at them, and again, if these were much better clocks than they are, they would not indicate the same time anymore. There's more time passing up here than down there. This is today there are clocks where, in laboratories, where this can be measured literally at 30, 40 centimeters of difference of height. So time is not the same at different altitudes. What happens is that there is the Earth has its own gravitational field, its pull, and the Earth is a big mass, and the mass slows down time. Masses around them slow down time. Time passes more slowly. The effect here is small, just fractions of a nanosecond. It's much bigger near Jupiter, because Jupiter is bigger. Is much, much bigger near a black hole, is enormous near a black hole. So if we could travel near a black hole, which is just an issue of money, right? I could go to a black hole, stay there half an hour, come back in the distant future. Because a lot of time has passed here, little time passes near a black hole. So there isn't one time. There are always different times. Now, we know that. We have been knowing that for a century because this is an immediate consequence of Einstein's general relativity. But it's only today that we have clocks in which we see that happening concretely. In fact, so much that the GPS would not work if this difference of time passing up there to the satellite and here would not be taken into account. A second consequence of that, which is perhaps the most dramatic of it all, is that we have learned that the notion of now, of present, okay, I said all the universe is in a now and passes from time to time. Now this is wrong. It's wrong in a strong sense. What do we mean by now? I watch you, you watch me, I see you now, you see me now, we are in the same now, right? That's the now. And we know what we mean by now because I have my time, you have my time, but it's clearly the same because I can see you, you can see me. But if you think for a moment, that's wrong because I watch at you, I look at you, and light takes some time to travel from you to me. It's a very short time, but nevertheless it's some time. So I don't see you now. I see you a few nanoseconds ago. It takes 3 or 4 nanoseconds light. So when you're looking around the world, you're seeing the past. You're not seeing the present. Okay? Everybody sees the past. And everybody sees a different past because everybody in a different position. Lights take time. Now, I see you in the past. In the moment I see you, you can look me seeing at you, but you, the moment you see me seeing you, is few nanoseconds later than when I see you. So this idea that we are in the same present, we have it only because we disregard these nanoseconds, which we can, because for us nanosecond is nothing. And if somebody's in Beijing, it's millisecond, it's still nothing. So we can think we are in this common present. But as soon as we, I hope will happen, as soon as we start traveling outside the planet regularly, we did a little bit in the 70s, but then we stopped. As soon as we start doing it again, as I hope will happen, we will rapidly realize that when somebody is on Mars or on Jupiter, asking what this person is doing right now doesn't make any sense. Because it takes 15 minutes light from coming, say, from Mars to here, and 15 minutes back. So we cannot have a common now, a conversation. Hi. Half an hour. Hi. Right. In between this half an hour, when is the now? Well, we can give some conventional definitions, but no one that works objectively in an objective manner. So the very idea of now makes sense locally. Here and now makes sense around me. But now in the universe has no meaning. So the question, what is happening now in a distant galaxy, is a completely meaningless question. It's like asking, what is happening here in Beijing? The stupid question. Here is here, it's not in Beijing. Okay? Which has huge implications because the reason I was in California is because there was a conference on the nature of time. There were physicists, there were philosophers, there were brain scientists, psychologists, and the philosophers are still struggling with that. The good philosophers, those who listen to physics. And the good physicists, those who listen to philosophy, right? They were there, they were talking, because that's how knowledge goes ahead, when we listen to one another. You see, we're used to say reality is the set of things which are now. But if now doesn't make sense far away, how do we think what is real? We have to rethink the meaning of what is real. Real now doesn't make sense. Real now here makes sense, but it's for us, obviously. So you see how this question start touching everything. Now, these are things we have learned in the past century. When we try to bring together this knowledge of the complicated structure of temporality with quantum mechanics, things become even more complicated. Because quantum mechanics tell us that clocks can be in superpositions of different readings. So something can be in the past and also in the future at the same time, in this funny way in which Quantum mechanics allows superpositions to happen. Quantum mechanics tell us that quantities are discrete in the small, so any clock, any temporal, any measure of time of any clock has a minimum value. It's called the Planck time, 10 to the minus 44 seconds, a very small amount of time, beyond which there is nothing. So all our ideas of time that is continuous, that is universal, that is unique, they all have to be abandoned. In the theory in which I work, which is loop quantum gravity, which is one of the attempts to solve the problem of mixing generativity with quantum mechanics, we have a set of equations. We're not sure as the final story, we're not sure of the real ones. We're trying to check, we're trying to look for experiments to confirm them. But these equations have no time variable at all. So at the most general level, fundamental level, the description of the world that I and a number of my colleagues think works is without any notion of a time variable. So the best way of, it's like, time is a very complicated stratified notion. You take away unicity, you take away the globality, you take away continuity, you take away all these pieces, at the end what remains is almost nothing. And so you describe the world with a number of variables, the relation between one another, without giving a time variable in which evolving everything. So the second part of the book is this, how I think the world can be understood at this fundamental level without time. The third part of the book, and I get to the end, in my opinion is the best. It's the most confused one, the less clear, because we all have less clear this, is how you go from this physical, very wide understanding of a world without a fundamental time to our sense of time, right? Because then it's not sufficient to say at the fundamental level there's no time. So then what it is that we call time? We have to go back. And we have to understand all the properties of time. Where do they come from? And some come from approximations. Okay? Time is discrete, but it's little chunks, but they're so small that we look at large and we don't see the chunks, so we see it continuous. That's pretty simple. So we say continuity is just an approximation. Our clocks measure different things, but the differences are so small, so we ignore them, so we talk at a single time, and so on and so forth. But the various aspects of times that are so natural to us, they come at different levels, and they're studied by different science. It's not just physics. It's not just mechanics. It's not just quantum mechanics. There is statistical mechanics. There's a big problem at the core of physics of why the future is different from the past. The equation of physics don't seem to distinguish the past from the future. So a big part of the book is devoted to that, to explain why there's a big problem, and some idea which I have on the perspectival aspect of the difference between the past and the future, which I don't want to go into because it will open a long discussion, and I'm not very sure is correct, but I try to illustrate in the book. All the way, and I think this is perhaps the most interesting aspect, to the fact that what we call time and what confuses about when we think about time is not so much the reading of the clock, the physical time, but is what happens in our mind, in our brain, when we think about temporality. And this is something that philosophers have been saying for a while, starting from St. Augustine, and Husserl has been insisting on that. When we think about time, what we're really thinking about is the memory we have of the past and the anticipation of the future. St. Augustine talks about music and says if you listen to a phrase, a musical phrase, you get a meaning from the musical phrase. But think a moment, you only hear one note, because in one moment there's only one note. How do you get from one note to the full phrase? Well, because you remember the previous notes and your brain anticipates the next one. When we think at the time, we think at what happened yesterday or the day before or 10 minutes ago or what may happen tomorrow. We have memories oh, we read book about the American Revolution, the formation of the Earth, the Big Bang. So the time that we think about is not so much the physical time, but the memory we have about it. I talk a lot about Proust in the book, because Proust wrote this fantastic novel, which is all about time. Even the title is Time, La Recherche du Temps Perdu. I don't know how it's translated in English. Yes, Remembering Things Past. Thank you. The literal translation is The Search of the Lost Time, the literal translation of the French title. And it's 3,000 pages novel, full of stories, character, consideration, happenings, but is not presented as happening in time. It's all presented as in the memories of the main character. It's all here, between the 2 ears of the main characters. It's all in the circumvolutions of the brain. And I think there's a deep intuition here. Time confuses us because what time is for us is what our brain does with time, which is connected, of course, to physical time, but the brain does much more than that. The brain uses the property of physics, uses thermodynamics, uses entropy to store... 111. Okay. To store information and memories, and constantly anticipate the future. There is a book by a neuroscientist, it's called Dean Bonomano, recent, about the function of the brain, and the title is Your Brain is a Time Machine. This sense of flowing, this sense of passing, we associate a speed to the time that passes. Right? Sometimes it passes fast, sometimes it's slow. Obviously, time doesn't have a speed. 1 second per second is not a speed. That has to be understood studying the brain. And I think there are a lot of philosophers and physicists, some of my colleagues, some of my best friends, who confuse the sense of flowing, which is in our brain, with fundamental physics, and want to find in fundamental physics, which is not there in our brain. And finally, and perhaps this is why time fascinated so much all of us, me at least, time is not emotionally neutral for us. Time is heavily emotionally charged. Time not only opened up the future, we are time. Our way of being is being in time. Because our brain is something that works in time. And time is also what takes us away everything, including life, right? So in Buddhism, the first truth is that life is sufferance, and the second is that life is sufferance because we have difficulties to deal with impermanence, with time, with the fact that we lose everything. So we cannot think about time deeply without feeling the emotion of time. And I think that, see, Reichenbach, the great American, great analytic philosopher who studied time, as one of the best books about time, he said a lot of philosophies about time are colored by the desire to deny the reality of time, from Plato to Hegel to Parmenides, because time is fearsome somehow. I think that this emotion of time is not so much a fog that prevents us to understand what time is for real. It's very much what time is for us. So to understand what time is for us, this sense of flowing, this sense of passing, this opening, this clearing, Heidegger called it clearing in which we are immersed, some past, a little bit of future, in which we are. We live in time, the time in which we live. This time is in part physics, in part thermodynamics, in part statistical mechanics, in part brain science can tell us something, but especially is our emotion about time. So to a large extent, the emotion of time for us is what time is for us. Okay, I've given you a hint of what is in the book, and now I take your questions. Or thank you. How am I doing with time? Okay. Please use the microphone there.
Thank you for being on time today at Politics and Prose. I have been on and off an aficionado of MacTaggart who denies that there's such thing as time. It's our concept. And I've struggled with that and his ABC lines. So could you at least make MacTaggart a little bit the denial of time, which it makes sense to me. It doesn't exist. We are the ones that perceive it. So that's all I have to say. Could you please clarify that? Thank you.
MacTaggart is a philosopher who wrote a very famous article on the nature of time, 1908, probably. So nothing to do with Einstein. It was just after special relativity, but I don't think MacTaggart knew the special relativity. And the point of the article was to show that time is not real, does not exist. Time is false. And let me take away the C series, simplify. He has two ways of thinking about time that he called the A and B, the A series and the B series. A series is time in the sense now, future, past, so time with a now. And B is before and after, so temporal relations only relative to something. So before Tuesday is before Monday, no, is after Monday, May is... and he has an argument to say, he wants to call real time only the A series, and has an argument, a detailed argument, to show that the A series is contradictory. It leads to regression to infinite. And therefore, A series contradictory, A series needed for time, and therefore there is no time. Let me tell you my take. It's not only my take, it's other people on that, but I got convinced. I've struggled with that paper with MacTaggart a lot. I think that time is well described by the B series. So forget relativity, forget quantum mechanics, forget all the rest. It's completely described by the B series, and that's it. But it's not true that the B series does not describe time. The B series is time. The point is that we see time from the inside, never from the outside. When we say now, it's always now with respect to us. It's now for me, for you, now here. There is no time now with respect to somebody who is outside time. The A series, the distinction between the A series and the B series, assumes that one could step out from the sequence of events and in the sequence of events see a sort of now moving on it. But that's a mistake, because there is no now moving on the sequence of event. There is just a sequence of event. And since we don't see it from the outside, we see it from the inside, we are always somewhere. So now is always lexical, is always relative. So I think, and I agree with those philosophers who think that the solution of MacTaggart puzzle, if you want, is that A series is a bad description of time. The notion of now is only indexical, is only relative to a point of time, and it describes time. It's not that it does not describe time. Sorry for being technical in this. The question was very technical.
On a much lighter tone, would you comment on Einstein's quote that while kissing his girlfriend, an hour felt like a second, but sitting on a stove, a second felt like an hour?
Yeah, Einstein said it tongue-in-cheek, of course, and was joking a bit. But let me put it this way. We all know that psychologically 1 hour can be very long or very short. It's part of our experience. Then we went to school and we were told that time is the same for everybody and is measured by clocks, right? And so we've been schooled into thinking that beyond our flexible perception of time, there is a true real time, the time of physics measured by... Well, it's not true. It's true to some extent, because physical time itself, it's much more flexible than what our school book on physics told us. Never take too seriously the school books. they lie.
Since we have CPT theorem, CPT symmetry, that is we believe to be a exact symmetry of the nature, and CP is already violated, so we assume that T has to be violated. So you are saying that there is no like kind of perception of time, and if the T symmetry is violated, how is that incorporated in your description of time?
Yeah, thanks for this question. This is a point that has raised confusion often. The world is not symmetric. Physics is not symmetric and T going to minus T, period. It's symmetric under T going to minus T and some other thing, okay? Even without CPT, already in classical electromagnetism, if you take a solution of Maxwell equation and you just read backward in time, is not a solution of Maxwell equation. You have to flip the magnetic field, right? So, and this has, David Albert has written about that. There's been some discussion about that. I think that as far as we know, CPT is a symmetry of nature, at least in quantum field theory on Poincare it is. And so when I say invariance with respect to flip of time, I mean CPT. I don't mean T alone. That's what puzzles us. The world ahead in time and the world backward in time with a B flipped, with a charge flipped, with the proper things flipped, are indistinguishable. That's the puzzle, not T alone.
Hi, my question is less technical, but I was just wondering, in your own life, how do you kind of develop the skill of writing to the point where you felt kind of comfortable writing these books?
I don't know. I have not been. I started writing very late. I've been a theoretical physicist period until, well, in my 50s. And I started writing late. However, I've been reading all my life enormously since I was in my 20s. And not just reading physics, reading everything. I read novels, I read literature, I read classics, I read philosophy, I read all sorts of stuff. And I've been, writing for myself, not books, since I was... I never thought of writing books for the public. I think that having done a lot of reading and a lot of just pleasure writing for myself has helped. But look, let me put it this way. I could never write a novel, so I'm not a writer in the sense. And in fact, in Italy, in my school, we had some school exercises which was called composition, in which you're given a topic and you have to develop. And I was very bad at the beginning. I became good only when there was a topic in which I had something to say. And I think it's the same with my writing. If you ask me, write a good piece of three beautiful pages, it's going to be horrendous, okay? It was a night, stormy, and nothing else comes to mind. But if I have something to say, then I find the right words to say it in a way that goes through.
When you gave the example of the difference in our concepts of time for someone who travels, say, to Jupiter, and how
Yes.
you think eventually we will have to come to terms with that, I immediately wondered, well, what does that mean for how one ages? Does one age differently because the concept, the time that's passing is different?
Yeah, I mean, if you're going to be a civilization with some interstellar travel and fast travel, then we're going to be used to the fact that our age differences are going to vary. So I can, young guy much younger than me, maybe I go for a trip and I come back and he's much older than me. So each of us age differently. Of course, for each one of us, 1 year is 1 year, 50 years is 50 years. It's not. So for each one of us, like lifespan is.
So that if a person hadn't, you mean there would be no difference in that individual person's
correctly.
aging?
Correctly. So,
Okay.
so I for what physics is concerned, I mean, the time that I have for writing, for thinking, for living is just whatever it is, whatever my biology allows me. It's not going to be stretched or delayed. But the same amount of time would correspond to a different amount of time of another person. Obviously, if we go there, we'll have to readjust our way of thinking, right? I mean,
Okay.
if I have I don't know, if I have a girlfriend much younger than me, I can go for a trip and come back when she's my age.
So I guess from the time I was a relatively young child, I've understood the concept that if you want to travel in time, the only way you could do it was to approach the speed of light. And now you've introduced the concept of gravity having an effect.
Yeah, it's a second way of traveling time, right.
And that was my question. Are these two different lenses on the same phenomenon, or are they completely separate mechanisms?
The first one, the one you knew, is what was understood by Einstein in 1905 with special relativity, and clearly understood by him. In fact, is that essentially he understood, because equations were already there, written by Lorentz and Poincaré. The second one, so the difference in the passage of time according to where one is due to gravity, and it is understood in general relativity, and it's a consequence of the fact that the structure of space-time is affected by gravity, by masses. So, from this perspective, there are two different things. They are not so much two different things, because once you go to general relativity, in general relativity, the passage of time is determined by some integral along a world line, so it subsumes both of them. They become two aspects of the same thing. There's just no single time. The only thing that exists is the time along a path in space-time. So whether it's a path that stay put near a black hole or that move very fast and comes back is the same equations.
Quick follow-up question. Is it wrong to think of time as distance to the Big Bang?
No, you can, but it's just one of the many ways of... let me give you an example. Let's say that we want to label the event of the universe the distance of the Big Bang. So imagine at the Big Bang we have many clocks, and each one measures its own time. So then we say now is what, 14 billion years and something after the Big Bang. So we say that there is a... When all the clocks... The events where all the clocks indicate the same thing are a common time. That's a definition of a now. It's a very bad definition. If you think for a moment, it's a horrendously bad definition. For instance, we are here on the Earth, we're inside a galaxy. So because we're inside a galaxy, we're in a potential well, so time slows down with respect to outside the galaxy. Okay? So right now, if you go just a little bit outside the galaxy, the time from the Big Bang here and the time from the Big Bang there are completely different. So if you're there and come this way, you jump into the past. And if I just go out of the galaxy, I jump into the future, which means that it's not a very good definition of past and future. You see what's going on? So it's a conventional way of giving names to events that does not correspond to nothing physically meaningful and actually contradict other ways of thinking about time.
I just wanted to ask something about not time but loop quantum gravity, where you have like the granular structure of quantum time. I mean the geometry of the space and time or something like that. Do you think like it's going to be proven in some of the like cosmological phenomena or something really soon, or how is the progress going in applying loop quantum gravity to some of the observed phenomena?
Yeah, thank you for this question. I don't know. I hope, I would like to answer yes. I would strongly like to answer yes. I think it's going to happen soon. But I'm not sure at all. I'm working on that. There are many groups that work on applying loop quantum gravity to early cosmology. We and others are applying loop quantum gravity to black holes. We know that black hole shrinks because of Hawking evaporation, and nobody knows what happens at the end of the evaporation. People say, oh, at the end of the evaporation, the black hole pop, disappears. But that's nonsense, because we don't have a theory for that. And in fact, we think that that's wrong. The black hole don't just disappear. We think that what the theory is saying is that they tunnel into white holes, and so there could be observable effects on that. So there's a big work now. Now we have sort of the equation of loop quantum gravity written down. There's a big work of trying to pinpoint where we could see, as you say, an observation that could confirm or disconfirm them. I hope before dying that of seeing a measurement and say yes, this is what's going to happen. It's not that. Let me just add one thing. It's not that we have no empirical information on quantum gravity. We have a lot, but indirect, nothing very strong. We have the confirmation of Lorentz invariance at a very high scale, which has ruled out quantum gravity theories that violate Lorentz invariance. We have the recent neutron star merging that was observed by gravitational waves and in the optic that ruled out a lot of theories that have the speed of light different than the speed of gravitational waves. We have the lack of observation of supersymmetry at LHC, which ruled out at least the theories that require supersymmetry at low energy. So information is coming in, but nothing that for the moment could say, okay, that loop quantum gravity is a good theory or something like that.
One follow-up question. Do you think, we understood classical electrodynamics in classical background before the formulation of QED? Do you think, can we understand most of the phenomena of gravity just by considering fields in classical background and not requiring it to be a quantum force with, graviton being present or something like that? Can it be a classical force in quantum background? Classical background?
You mean as a fundamental theory?
Yeah, as a fundamental theory.
Okay, so no, I think that's very unlikely for a number of theoretical reasons, and there are some experiments that are being mounted that a couple of different groups have proposed very detailed measurements that could prove that someone could test the possibility of putting the gravitational field in a superposition. And I think that would be definitive if these experiments are made, as I hope they were going to be made in the next years. I'm ready to bet 97 to against 3 that they will say that the gravitational field is a quantum field like all the others.
I have 2 questions. My first is, when you think of time, what comes to mind?
The brevity of life.
My second question is, in 7 Brief Lessons of Physics, what do you mean by when you say you don't get anywhere by not wasting time?
Oh, I'm glad that you asked that, because the first question you asked me, I gave an answer was probably not appropriate for you. I mean, for you, time is a long, great future. So for you, time is opportunities, not. But this second question, the other way around. Look, at the beginning of the 7 Lessons of Physics, I talked about Einstein that was wasting time when he was a young man. It was implicitly talking about myself in reality. I wasted a lot of time when I was young. I did not hurry. I studied, but I followed my curiosity, I followed whatever came to my mind, And I'm very glad I did that. I think nowadays society put enormous pressure on young people to do this and this and this and that, stay in the rails. And one has to go out of the rails if one, in my opinion, if one wants to do something good in life.
In the 7 Lessons book, the 6th chapter, I found very intriguing and confusing, the one on heat. And this one sentence, as soon as there is heat, the future is different from the past. Do you expand on that in the current book, or?
Yes, a lot, but I'm afraid I'm going to confuse even more. Because I try to make sense of that. That's one of the, what I said is one of the big open problems in physics. Let me be precise about that sentence. That sentence is a very specific observation. Namely, if you have a physical phenomenon, whatever phenomenon you want, and you film it, you take a movie of it, and then you show the film backward. Okay, suppose I have a pendulum. I'm going to break a cup for sure. Hope not. You take a movie of this, okay, and then you show the movie backward, and you see something absolutely normal. There's nothing funny about it in going backward, okay. But if you wait enough, and after a while this stops, and then you show it backward, there is something funny because it starts moving by itself. Okay? So in the first case is a reversible phenomenon. A phenomenon can happen backward in time and is still reasonable. In the second case, when it stops, is a non-reversible phenomenon. Well, all non-reversible phenomena have heat. The reason this stops is because there is friction, and friction heats a little bit the... If I throw this, it stops because there is friction and it has heated a little bit the table. Okay? So, and that's always, anything which is oriented in time involves heat. And heat is what? Is the movement, the fast movement of molecules. So what's really going on here is that I throw this, and the movement of that is passed to the molecules of the table. The molecules of the table start moving, but in a disordered way. So is an issue, is an instance of the world getting in disorder, so to say. And the extraordinary discovery of the physics of the 19th and 20th century is that this is all there is about irreversibility. So the difference between the past and the future is only that. Is things getting, I'm simplifying a bit, but is things getting heated up, getting disordered, and that's the meaning of entropy going up. It's mind-blowing. I mean, is possible that the difference between the future and the past is just disorder? Well, it is. I mean, the reason we have memories of the past and not memories of the future is only this disordering of things. The reason we consider the past fixed and the future open is only the fact that in the past there was more order and so on. So you find it puzzling, strange, hard to understand. So do I. And in this book also there are a couple of chapters in which I try to give a tentative explanation of that. And there are 2 short chapters, and at the beginning of the 2 chapters say, I write, if this doesn't make any sense, skip these 2 chapters and go ahead.
This might be sort of follow-up to this. Do you have a brief conceptual description of how a fundamental particle would experience time? Is it like truly discrete, or something like Alfred North Whitehead's, it's more like a fuzzy number?
Taking of this, of course, metaphorically, sufficiently metaphorically. I think at the fundamental level, there would not be anything like a continuous time evolution. So I think nature in its elementary physical level, it's granular, so it can only be discrete. It can be a sequence of discrete steps. And so, of course, a particle doesn't have experience, but it interacts with the rest of the world in discrete steps with a probabilistic relation one to the other. That's the closest I could say to your question. Hi.
I was kind of wondering, what if the Big Bang was an echo of a previous Big Bang and was an echo of a previous Big Bang? What phenomena is likely to be common to, such as, for example, a black hole? Would there be black holes in each Big Bang? Right. And the other thing are there any overlaps between quantum mechanics and biology that are discussed?
Yeah, so the first question is, I know the answer is easy, and the answer is we don't know. Let me be more specific. We know very well the history of our universe all the way to the Big Bang, so up to the Big Bang. And what happened there, we don't know. So it might be that in some sense time started there. It might be that there was a previous universe in some sense. We're using loop quantum gravity to compute. People working on that tend to find it more plausible that there was a sort of previous universe that contract and then expand. Then you ask, what about before? I don't know. We're trying to see a little bit over. But it's open. It's completely open. And you asked, could there be black holes in the previous universe? Well, I finished a technical paper that I posted online 2 days ago about the possibility of black holes going through this the Big Bang, which is not a Big Bang in that case. It's a big bounce. So the universe bounces up, sort of. It's a very speculative paper. I'm not sure at all. It could be, in fact, the idea is that this could be one possible explanation of dark matter. It might be found wrong next week, it's possible. The other question, I have more clear ideas. The relevance of quantum theory to biology. I have found nothing that makes me believe that quantum theory is relevant for biology. Nothing. There's a lot of speculation about that, including good people like Roger Penrose. I'm not convinced. Of course, quantum theory is quantum theory. It determines the atomic forces, the molecular forces. So quantum theory, it's all over. But it what keeps matter together. So everything is quantum theory if you want. In that sense, yes, quantum theory is. But specifically, I think that we're going to understand biological phenomena just in terms of basic chemistry, not as specific manifestation of quantum theory. I'm not sure about that because there are people who are exploring that. So it's good that people explore that. There's some serious attempt to see whether there's some idea in nanotubules that there is some quantum coherence, but it's not very convincing. I mean, we are hot, and quantum effects tend to dissipate very rapidly. It's very hard to maintain coherence. So I know for a fact that if you go to the internet and search for quantum theory and life, quantum theory of intelligence, quantum theory of biology, you find all sorts of things, and that's all crap.
So we have time for one more question.
If I'm hearing you correctly, it sounds like, popularly speaking, one of the problems in dealing with time is that human beings have an emotional life connected to change, and in particular, you said something which kind of struck me was our emotional attachment to organization and disorganization versus past versus future. If I'm understanding you correctly, then the next question is, will it therefore be necessary in order to understand quantum physics better for human beings to transcend their emotional life for change in order for them to more clearly understand and perhaps get better answers for what's going on?
Yeah, thank you. No, not at all. Somehow it's the other way around. I think that there are some questions we pose about the nature of time. Let me make an example. I have some colleagues, they're a minority, but there are some colleagues, and they're both in physics and in philosophy, who say, I look at physics, and in physics, the physical equation talk about movement, but movement is just different position at different times in physics. And I can have, I don't know, here, different colors at different locations. And it seems the same. But here there is nothing temporal. Color change with position, position change with time. Well, one temporal, the other is not temporal. So is physics missing something deep about the flowing of time? Is physics not capturing the reality of the flowing of time? I think that's wrong, because when we think about the flowing of time, we're thinking about our emotion in time. So I want to disentangle, and what is physics, what is our emotion is our emotion. So if you ask the question, what is time in general, everything comes in. But if you ask physics, it's physics. If we ask chemistry, it's chemistry. If we want to say quantum mechanics, quantum mechanics. It's nothing to do with our emotions. It's exactly the opposite of what I'm saying. Let's disentangle the issues, but be aware that in our perception of the world, we see the world from the inside, not from the outside. We are not gods outside the universe. We are inside the universe. So we are located in a point of space. We are in a moment of time. We have an emotional connection. We have time machines that work. So if we are confused about time, let's remind ourselves that we are emotions even before than being rational. But then when we have to understand chemistry and quantum mechanics, it's our rational part that helps us to understanding what is going on. When we have to understand our friends and our own life, is the emotional part that matters. Thank you. Thank you very much.